Welcome to the deep dive. Today, we're taking a really close look at the rulebook for electricity, the National Electrical Code, specifically the 2023 version, NFPA 70.
Mhm.
And our mission isn't just a casual browse. We're doing a proper deep dive into one kind of surprising specialized rule. It's one that can actually save a lot of money on big projects by letting designers size equipment correctly.
Right. And we're heading straight into Chapter 2, Wiring and Protection.
Hmm.
This chapter is really the bedrock for safe installations, making sure wires don't overheat, circuits are protected.
Yeah, the safety basics.
Exactly. But it's also where you find the methods for load calculations. These are crucial. They tell you exactly how much electrical capacity a building needs, and that dictates how big and how expensive the infrastructure has to be.
And that's the key, isn't it? Because if you're designing something huge, like a hospital or maybe a big data center, or like we're talking about today, a school,
Mm-hmm.
you just can't afford to plan for every single light, every outlet, every motor running full blast all at once.
Oh, absolutely not. That would be incredibly wasteful, monumentally so.
So that brings us to this specific rule, Section 220.86. It's called the optional school feeder load calculation. Kind of specific, right?
It is, and it's a fantastic example of the NEC really adapting to how buildings are actually used. A school's energy use isn't constant like, say, a factory running 24/7.
Right. It has peaks, downtime.
Exactly. Lots of diversity across the whole building. So this optional method, it lets you calculate the load differently than the standard, very conservative methods you find elsewhere in Part 3 of the article. It offers immediate efficiency.
Okay, but why schools? Why did they get this, special calculation? Is there a catch, a condition they need to meet?
Yes, there is a very specific condition. The source material is clear on that. This optional calculation is only allowed if the school has electric space heating or electric air conditioning, or both.
Ah, okay, so it needs that big electric HVAC system.
That's the key requirement. Because having that kind of system usually means the school has these major definable seasonal electrical loads. They often drive the biggest power demand. And that allows the code to make some, let's say, predictable assumptions about how diverse the rest of the load will be throughout the year.
Okay, so if a designer has a school project, it's got the electric HVAC. What actually goes into this connected load calculation? It must need to be pretty comprehensive if they're going to apply discounts later, right?
Oh, it has to be thorough,
Yeah.
definitely. The connected load needs to cover basically everything, all the lights inside and out,
Okay.
all the power outlets, water heating systems, any cooking equipment, other fixed loads, everything.
Gotcha.
And here's a really interesting point for optimization. When you look at the big HVAC loads, the air conditioning and the space heating, you calculate both, but you only include the larger of the two in the total connected load.
Ah, that makes sense. You wouldn't be running the heat and the AC flat out at the same time.
Okay, exactly. It's like a built-in efficiency based on, well, climate reality.
Right.
It immediately trims down that potential peak load figure.
Okay. Smart.
But, the NEC is also very precise about where this flexibility stops. We need to look at what's explicitly excluded.
Right.
The source material states very clearly,
Yeah.
this section, 220.86, it specifically cannot be applied to portable classroom buildings.
Huh. Okay, why not portables? What's the thinking there?
Well, portables often have different setups, different power distribution, maybe different load profiles, and crucially, they're temporary or modular. They just don't have that same massive, spread out diversity of load that you get in a big, permanent central school building. The code recognizes that the demand factors we're about to talk about, they just wouldn't be accurate for those smaller, more isolated units.
Got it. So let's get to the heart of the savings then, this idea of a demand factor. It's basically the code saying, look, even if you have 100 things plugged in, maybe only 75 are likely to be on at once.
Precisely. It's acknowledging real-world usage. Not everything runs simultaneously. And Table 220.86 gives this very specific tiered structure for schools based on that idea.
And those tiers are key for saving money, right?
Absolutely. The tiered structure is where the optimization really happens. It recognizes that, okay, in a small area, the load density might be high, but as the school gets bigger, the usage becomes more spread out, less simultaneous. The calculation uses the total connected load, but it's expressed in VA per square meter or VA per square foot, load density.
Okay, let's break down those tiers. How much does the required capacity actually drop?
So there are 3 tiers. Tier 1 is the baseline, the most conservative part. For the very first bit of load, up to 33 VA per square meter, or that's 3 VA per square foot, the demand factor is 100%.
Full price for that initial slice.
Right. That baseline load is assumed pretty much always on.
Then tier 2, this is where the savings start to kick in.
Exactly. For the next chunk of load, everything over that first 3 VA per square foot up to 20 VA per square foot, or over 33 up to 220 VA per square meter.
Right.
Or the demand factor drops quite a bit, down to 75%.
Wow. Okay. A 25% reduction. That's immediately going to mean smaller wires, smaller equipment upstream.
Instantly. Less copper, smaller conduits, potentially smaller transformers, and switchgear.
And then there's tier 3 for the rest of the load in really large facilities.
Yep. Any remaining load over that 220 VA per square meter mark, or over 20 VA per square foot, gets the biggest discount.
How much?
The demand factor there drops all the way down to just 25%.
Only 25%. Seriously.
Seriously. So for a really big school, a huge chunk of its calculated load only gets factored in at 25%. That's a massive difference. It's the code basically saying, okay, for a system this big, diversity of use is practically guaranteed, so we can size things much more efficiently.
That's a game changer for cost, I imagine. But, okay, here's where things can get a bit tricky, maybe. The actual formulas, when you look them up, they have these sort of fixed numbers added at the end.
Ah, yes, the fixed additions.
Right. So for the listener trying to follow, like for that 75% tier, it's not just amount by 75%. It's amount by 75% plus some fixed number. In VA per square foot, it's plus 3 VAF. Oh, wait, no, looking at the source. For the 75% tier load in VAF FT, it's amount by 75% plus 3. Let me reread. Oh, wait, the calculated load adds the baseline back. So for the 75% tier amount, it's amount by 75% plus 3 VAF tier. No, the source says the result adds the baseline. Let me check the source again. Okay, it's structured like this. Tier 1 is 100%. Tier 2 is 75% of the amount in that tier, and then you add the tier 1 amount. Tier 3 is 25% of the amount in that tier, and then you add the amounts from tier 1 and tier 2. The table itself shows the factors, but the calculation builds cumulatively. Let me try that again. The table shows the factors: 100%, 75%, 25%. But the formulas presented for the final load based on these tiers often incorporate fixed values that represent the already calculated portions. Is that complexity really necessary? Why not just apply the percentages cleanly?
That's a really good question. It does look a bit confusing at first glance. But those fixed additions, they're actually quite important for making the calculation work correctly across the tiers. They're not arbitrary. They're essentially performing a bookkeeping function.
Okay. Bookkeeping how?
Think about it cumulatively. Let's stick with VA per square foot. Tier 1 is the first 3 VAFTA at 100%. Tier 2 is the load between 3 and 20 VAFTO, calculated at 75%.
Yeah.
Tier 3 is anything over 20 VAFTO, calculated at 25%.
Right.
When you calculate the total load, you need to account for all the tiers correctly. The formula for the total load effectively says, take the Tier 3 amount times 25%, plus the full amount calculated for Tier 2, which was that segment at 75%, plus the full amount calculated for Tier 1, which was that segment at 100%. Those fixed additions you see in some formula representations are essentially pre-calculating and adding back the required load from the higher percentage tiers.
Ah, I see. So if you're calculating the total load and you get to the 25% part, the fixed number you add is basically the sum of the load already calculated at 100% and 75% from the lower tiers.
Precisely. It ensures that the lower demand factors, 75%, and especially 25%, are only applied to the correct portion of the load, the part that actually experiences that higher diversity. It prevents you from accidentally applying, say, 25% to the entire load.
Okay, that makes a lot more sense now. It's not arbitrary. It's just ensuring each slice of the load gets its proper demand factor applied as you move down the scale. Less confusing when you think of it that way.
Exactly. It maintains the integrity of the tiered system. Now, moving just beyond the load calculation itself, the code ties in a couple of other related points for systems using this method. For instance, calculating the neutral load.
Okay.
The code permits you to determine the neutral load for these feeders and service conductors using section 220.61.
And why is that significant, allowing a separate neutral calculation?
Well, especially in typical three-phase systems you find in large buildings, the neutral conductor often carries much less current than the main phase conductors, assuming the loads are reasonably balanced. So using 220.61 lets the designer calculate that neutral load specifically. It often results in being able to use a smaller neutral conductor compared to the phase conductors. That's another layer of potential material saving without compromising safety.
More optimization. Okay, so bringing it all together, the so what for the industry. You use this optional calculation, you apply these demand factors, maybe size down the neutral. What's the big impact?
The big impact comes from a crucial efficiency clause related to the overall service size. The NEC states that the ampacity of any individual feeder within the building doesn't need to be larger than the total ampacity calculated for the entire building using this optional method.
Ah, okay, so the whole building calculation sets the feeling.
Exactly, and that ceiling is often much lower with Section 220.86. Imagine you run a standard calculation, very conservative, and it says you need, I don't know, 3,500 kVA, service transformer, and main gear. Huge, expensive.
Hmm.
But then you apply this optional school method with its demand factors. Maybe it calculates out to only needing a 2,500 kVA service.
That's a massive difference.
Huge. You're not just saving on the cost of copper wire. You're potentially downsizing the main transformer, the switchgear, the concrete pad it sits on, the room it occupies.
The footprint, the cost, the installation time.
All of it. It reduces complexity and cost significantly, all while being fully compliant with the safety standards laid out in Chapter 2.
It's pretty amazing, really, that such substantial savings can hinge on a few percentages in a table based on square footage.
It really is. So to kind of sum up the main point, Section 220.86 is a really powerful tool. It's performance-based, you could say. It lets designers swap out a standard, often oversized calculation for one that uses demand factors, specifically reflecting how a large school actually operates. Its efficiency literally engineered into the code.
Yeah, it really acknowledges the reality of usage. The gym lights are on, but maybe the library wing is quiet, or the kitchen is busy, but classrooms are empty. That diversity. Now, we mentioned the NEC has whole chapters for special occupancies, like Chapter 5. We've just seen how school loads, because they're diverse, can get down to that 25% demand factor for large portions. So thinking about other specialized buildings, what about places that can't have downtime, like a hospital or a major data center? They run 24/7, right?
Mission critical.
Do you think their essential loads also get some kind of demand factor reduction, or are they stuck closer to 100% because they have to be always on? Are there other hidden efficiencies tucked away in the code even for those critical places?
That's a great question to ponder. The NEC is full of these kinds of specific adjustments for different building types.
Definitely something to think about next time you walk into a large, complex building. What kind of calculations went into sizing its electrical backbone? Anyway, thanks for joining us on this deep dive into the code.